Okay, let's continue with the simulation. So let me share my screen again. Um, okay, perfect. So let's go back to the simulation where we finished by getting the solution of the magnetic fields. Okay, and we finished by having a nice magnetic flux densities on the device, and having force versus current calculation. Okay, so now the next part is going to be doing the solution for the solid mechanics. For the solid mechanics, we need to add a couple of more constraints. Okay, the first one is going to be the fixed constraint. So this edge here, that is the silicon wafer, is going to be completely flat, and is going to be like attached to the frame for the to the table, for example, and it's not going to move. So it's going to be the fixed constraint for this one. Now we're going to apply some roller on this side because we know that this axisymmetric, in this axisymmetric, the magnet is going to move up and down and the membrane is going to vibrate. So this part needs to be on rollers and needs to be moving around. Everything else is going to be the axisymmetric or the axial symmetric is going to be on this one here. The final part is going to be the body load. So for this step only, we are going to define the body force as the solution of the forces calculated on the magnetic problem. So I will, if you do the force versus current simulation, you will know that the force is the global variable called Fmac, but the right name inside COMSOL is MF. This is because is the solution of magnetic fields, or magnetic field MF dot force in Z as a characteristic, a force in Z underscore Fmac, and the name of the variable that we define under the amperes calculation, sorry, on the force calculation, we define here Fmac. So we give it any name here. So under the mechanical constraints, you should include that body load. I'm going to make the other force in the R direction as 0. But in the C direction, I'm going to use this force here. Okay? And that's it. And again, the magnetomechanical should solve these two only. And the study that I'm going to simulate, it's going to be, if I do the stationary, is going to only solve the solid mechanics. Okay? I'm not going to solve in this step anything related with magnetics, only about mechanics. But I'm going to tell the software is, please use the values of the variables not solved. Okay, in this case, it's going to be the Fmac. It hasn't been solved as a user control from a solution of the study stationary. It means the stationary state that I calculated before, use it as a solution. So that's calculating the Fmac, storing that variable Fmac in some safe place in COMSOL, and then use it as an initial solution for the mechanical part. This is the way that we can couple these two physics. Again, it's an approximation. It's a valid one. It's good enough for some applications. It depends on your special research if you want to be more concerned about the dynamics. But for me, it's a good enough simulation. Okay, and please give me. I'm gonna use on top of that. I'm gonna do a parametric sweep of the current again. So I'm gonna have multiple solutions for different currents. So in this stationary solver, I please add all the possible currents that you get. So again, in the first simulation, I did a parametric sweep of the currents. Same currents that I use in this parametric sweep, I should use them in this second parametric sweep that is going to be the forces. In this way, I'm going to, for every single current that I use to calculate the force magnetically, now I'm going to use that force related to that current to calculate the displacement. And that's the way that we couple these two things together. Okay, so this solution is going to be giving you now the stress. Okay, it's going to be sorry, no, it's this one. So it's going to give you a solid displacement. And of course, a solid displacement, now you can add here deformation, and deformation can have a scalar coefficient of 1. And now you have this one. And remember, if you want something that tells you if there is a compression or an expansion, you can go, instead of doing the stress von Mises, you can go the solid mechanics, and you can generate the strain, and you can get the elastic, no, sorry, it was the elastic strain tensor, and you can do the 2-2, and you can plot this one, and for example, you can use whatever traffic light and just do it as a linear symmetric. So in this case, everything that is in red is going to be under expansion. Everything that is negative in green is going to be under compression. So this is a way to visualize what things are what part of the actuator is under compression, what is on the expansion. And again, you're going to generate a 3D view. The COMSOL is getting only one simulation, a 2D, but it can calculate the 3D simulation that is going to look like this, because it's the rotation or the revolution of that face. And as you can notice, it's going to give you a solution that is deforming the membrane up and down. So that's the mechanical solution for this one. What do we want to get from this? We want to get a 2D plot of like this one, where you are doing the displacement as the current input. Okay, so now this could help us calculating the full model for the transfer function, or the transfer function of your lump element model. My input was current, my output is going to be displacement. Okay, if you notice, it's not linear, it's nothing that you can calculate, because there is a permanent magnet associated with this problem. But on some parts of this, I mean, you recognize kind of this plot. So for example, you can set higher than 20 milliamps, you're going to have probably this curve that is an exponential curve. For example, you can approximate this as a second order equation, and you can generate a function for this range as current and or displacement versus current, and that's what you get. That's what you want to get. If you want to have a full equation, well, you need to develop the full model. But for the first order approximation, this would be enough. At least this will tell us like what are the values of current that you need to start using to deflect this. Okay, and to get a full deflection. So if you are using lower values of current, you're gonna be just in this regime and it's not producing high displacement. If you're using higher values than 20 milliteslas, you have a nice developed model for the actuator. Okay, so now the final, I'm gonna stop here with this simulation. The final step is gonna be, let's analyze this in frequency. I'm not going to do a full simulation of the input as a current in frequency, but I'm gonna just do it a mechanical part, and that's what I want you for this experiment, for this exercise. And I create a new model. Sorry, that's spoiler here. So I have the new model, and I'm doing a new study. So every time that you want to do a new solution, just add another study, and in the same file you can add a new study. But I make it separated because I changed something that is very important, and I don't want to make confusions. The thing that you need to make is that you're going to simulate the mechanical in frequency. I don't want to simulate the electrical in frequency, because I know that it's a coil is not going to change so much, or except if I consider the inductance, and that's a separate problem that we're going to not care right now. But I'm going to care about the mechanical response in frequency for this part. So instead of using the solution that I have for force in frequency, I'm going to use a fixed force. So it means that before I calculate the force versus the displacement, and I know that approximately at 100 milliamps, I'm having something like 3.2 millinewtons of force. So okay, I'm gonna say like, okay, let's do the frequency analysis with that force, 3.2 millinewton. So instead of using this force, I can go right click and disable this one. And right now it's disabled, but I disable. And I create another body load, and I'm gonna make a constant 3.2 millinewton on that force. Okay, so it's a constant force. I'm not changing anything on the current, so now it's a constant force that I'm driving. And I know that I need 100 millinewton, but the analysis here is the frequency analysis. So that's why we need to decouple things and to get the information that we want on this on this exercise. So for that one, I just need to repeat a study, but this time I'm gonna do a frequency domain, and I can select a range between 1 hertz and 10,000 hertz. Yeah, okay, so I go here and I go choose logarithmic 1 to 10,000 hertz in steps of 100 per decade. But this time I go decouple mechanics. I mean, I deselect the magnetics and deselect the magnetomechanical, and I only want to simulate the mechanical force. So it's going to have only the vibration of the membrane, because that's what I need on this problem, a specific problem that I give. So the solution of this one can be you just right click a 1D plot, and you add a point graph, and you select a point. You could be the center of the membrane, and now you simulate the frequency of all of them. Okay, and for that solution, well, the full solution is going to look like this. Okay, so where these peaks came from? These peaks came from other orders, other orders of the resonance for this membrane and other frequencies that it would resonate. But we are not going to care so much about them. In fact, I'm going to care just about this area here. Okay, that it has like the second order that we have followed so far, and we understand that because we haven't identified any damping coefficient to the system. We haven't talked about damping coefficient with this one. So right now there is no damping. So with no damping, you have a clear association on almost infinite displacement at the natural resonance frequency of your device. Okay, so it's something like this. But that's unrealistic. Like you are gonna have a damping, and we already saw that this is energy losses in the system. I'm just gonna avoid discussing the damping right now, because what we want to get out of the system is going to be precisely what is the mass associated with the membrane, and what is going to be the spring constant associated with the membrane. We know that if the damping coefficient is added, try to do it like here. If the damping coefficient, for example, is added, so now the plot is going to look something like this. More damping coefficient, and you're going to have more deflection here. You're not going to have this strong peak. Okay, so this is what we are going to get. Like, what is the maximum amplitude based on this, and what is the natural the natural resonance of the system? So you can calculate what is the mass, and you can calculate what is the stiffness based on the deflection or the spring constant of the system. Okay, so that's all for this. Now for the last part. Let me. Sorry. For the last part, that is kind of generating the model. Let me bring the Excel file here. And for the last part, that is generating the model. So you already have a frequency response. So we get a frequency response, and this is amplitude, and this is going to be the frequency. Okay, and from this you can extract what is the resonance, the natural frequency. Okay, and based on the natural frequency, you can get the spring constant, and you can get what is the mass of the system. Okay, but how this represents into how this is represented into the lump element model. So an overview of the lump element model is you are going to have a coil. So again, this is a coil that has many many windings on this side. Okay, this is kind of basically the actuator that you have. And inside the coil, you have a little magnet, and the magnet is attached with the membrane. This is what we have here so far. Okay, and this is moving up and down like crazy. Well, the coil is smaller, but I'm just doing a simplification. Okay, so first of all, the coil, you're gonna have a current source. So you're going to have a current source. This is going to be my current source, my inputting current. And I'm going to have a resistance associated with this coil. And I'm going to have the inductance associated with this coil. Okay. So from this model, you're going to have a current, and you can predict what is the voltage on each of the elements. Oh, sorry. And you can predict what is the voltage on each of the elements. Okay. And this is going to be my electrical model. Okay. Now, for the magnetics, and that's the part that we're going to cover in the next lecture, you're going to have a control. You're going to have a control source, okay, and that control source is going to give you a current. But in this case, the current is going through the air. So I'm going to have, here is my air, here is my magnet. It's going to go through the air. There is a reluctance associated, magnetical reluctance associated with the air. There is going to be a magnetic reluctance associated with the magnet. And there is going to be a magnetic reluctance associated with the coil. And this is a closed circuit that, I mean, the magnetic field is going to be produced like this, and it's going to close itself. Okay, so you're going to have a magnetic, this magnetic reluctance is called like the flow sign. Okay, and this is magnetic. So this here is going to be based on the current. So it's going to be a flow proportional, or a flow that is a proportion or is a function of the electrical current going through the circuit. Okay, so if you know the electrical current going here, you're going to have a flow, a magnetic flow. So this is going to be the magnetic part. The magnetic part. And the question that we posed for this exercise as that's going to be the homework, and I'm not going to give you the values, is now that you have this flow, the voltage associated with this electrical circuit, I mean, this is the magnetic representation, but I mean, it's the diagram is a circuit. These are called the or the electromagnetic forces. So every single component is going to express that you're going to have a magnetic flow, a flow of magnetic field, and they're going to be associated of or an electromagnetic force associated with that. And actually, that's represented kind of the voltage in the electrical component. So that it's what you're going to study, is what is the on this magnet here, okay? And that magnet I mean, now I can associate another voltage representation, another source representation, sorry. But this time, this source representation is going to be a voltage representation, okay? And this is going to be force as a function of this, of this ohm. This is going to be my ohm associated with that ohm, okay? And that's the mechanical component. That's the mechanical part that we already know how to do it. And it's going to have like, it's going to have a damper. Sorry, not damper, is just this. Yeah, it's going to be, this is 1/k, the spring constant. So this is the spring constant. You're going to have a mass, and you're going to have a damping coefficient. Okay, and again, this is going to be a source that is generating force, and the flow here, we know that this is x dot, and we know that the voltages on each of them they're going to be proportional to the forces. Okay, the force that you do on each of this one. Okay, so this is going to be the mechanical part. So the question for this is going to be, represent only the mechanical part, I mean, like only this portion, okay? And use the values that you model from here, that you model in the simulation. What is the K? What is the M? Okay, what is the omega N? What are those values on frequency, or in step? You can do a step response if you want in time, okay? And try to reproduce this part of the circuit, the mechanical part, okay? And that should be, and ideally, you can get out of this, I mean, if you do correctly and you evaluate all the parameters, you're gonna get your input as current in terms of S. Your output is going to be finally X in displacement. I mean, you need to derive this, the velocity, but you're gonna have X in displacement, and you're gonna have a full transfer function. And this is what you want to get. A transfer function that goes current, electrical current, as an input, and the output is going to be deflection. So this transfer function is for current input, and output is displacement output. So the full exercise is, if you have this simulation and you get some results from the simulation, what will be the model that we can associate with this simulation and that we can represent it in the lump element model? This is the question. What are those values that we can replace all of these components? What are going to be those values that we can use to model this transfer function that is input in current, output in displacement? Thank you very much. And if you have any question, please send me messages. I'm going to stop sharing here and I'm going to pause the record.